Okay, I was really unhappy with how I taught my lesson in the last block, so we're going to try reversing the order. We did like a little discussion of that, and then we went and did the video. This time we're going to do the video, and then we're going to do the discussion of that. So we'll see if that makes a better lesson. So we are on page 11, although I don't think it really matters because there's nothing for you to write down. Page 11. Do you guys prefer subtitles or no subtitles? Excellent. Okay, I think they're on already. Yes, they are. Okay, so let's watch what happens here.
In today's video, we're going to look at reversible reactions and see what we mean by the terms equilibrium and the position of equilibrium. Now, most chemical reactions look something like this, with the arrow in the middle pointing to the right, to indicate that the reactants can turn into the products. This means that it's a one-way reaction. Once the carbon dioxide is formed, it won't break back down into carbon and oxygen. In other reactions though, like this one here, we have a double arrow, which tells us that the reaction is reversible. The top arrow tells us that ammonium chloride can break down into ammonia and hydrogen chloride, which we call the forward reaction. While the bottom arrow tells us that the ammonia and hydrogen chloride can also combine to reform the ammonium chloride, which we call the backward reaction.
Or the reverse reaction.
So because both of these can happen, we call it a reversible reaction. Now, the important thing to understand is that the forward and backward reactions can take place at different rates.
If the forward and reverse reactions are taking place at different rates, what can you say about the system? It's not at equilibrium.
At the beginning of the reaction, there'll be loads of ammonium chloride, but no ammonia or hydrogen chloride.
So when they're saying at the beginning of the reaction, if we have loads of ammonium chloride, what we're saying is we've placed some ammonium chloride into a closed system, and we have placed no NH3 or HCl into that system. So we're just starting with reactants. What can you say about the forward rate compared with the reverse rate here? Forward rate is, if I have lots of reactant, concentration of reactant is high. What's the forward rate going to be like? Fast. Concentration of the product is nothing. What's the reverse rate going to be like? It's going to be not even just slow. If there is none of this at all, it will be zero. There will be non-existent reverse reaction at the beginning.
So the forward reaction will be really fast, but the backward reaction won't have started yet. As the reactants turn into products though, the forward reaction will slow down and the backward reaction will speed up.
Does that make sense as to why? As the reaction proceeds, we start making products. So all of a sudden, instead of having zero reverse reaction, we're going to have something happening, yes? And as we make more and more product, the product concentration increases. What happens to a rate when concentrations increase? It gets faster, right? Because there's more particles to collide. So the more product we have, the faster the reverse reaction. Yes? While we are making product, what's happening to the amount of reactant? It's decreasing. So what's going to happen to the forward rate? I now have less of these particles, therefore there will be fewer collisions, and therefore the forward rate will be slower. So, going through that one more time, if we start with all of this and none of this, forward rate is fast because we got lots of this stuff colliding, and we got none of this stuff colliding, so the reverse rate is nothing. Now, we start making product. That means that product concentration is increasing. Therefore, there will be more collisions between product molecules, which means the reverse reaction will speed up. How do you make products? You make products by using up reactants. So what's happening to the concentration of the reactants? The concentration of reactants is decreasing, which means there are fewer particles, which means there are fewer collisions, which means that the rate is going to decrease. So we start with a fast forward reaction and a non-existent reverse reaction. The forward rate gradually slows down. The reverse rate gradually speeds up until eventually the two rates are the same, equal.
After a while, the rate will even out, and the forward and backward reactions will be going at exactly the same speed. At this point, the concentrations of the reactants and product won't change anymore. So
Does it make sense to you that that once the two rates are equal, the concentrations do not change anymore? Because you're making product as fast as you are using it up. Okay? You are making reactant as fast as you are using it up. So those concentrations remain constant once the rates are the same.
we can say that the reaction is at equilibrium. So to clarify, at equilibrium, both reactions are still happening, but they effectively cancel each other out. So there's no overall change in the concentrations of the reactants or products.
Now, what do we call an equilibrium where the reactions are still happening? What kind of equilibrium is that? Dynamic. Okay, what does dynamic mean? Moving or changing. What's happening? Reactants are changing into products. Products are changing into reactants. But overall, is the concentration of reactants changing?
No.
No. Is the concentration of products changing? No. Okay.
Of course, in reality, the molecules are still breaking down and reforming, but because they do so at the same rate, there's no overall change in the concentrations.
Concentration is an example of what type of property? Macroscopic. Concentration is a macroscopic property. It's something you can either observe, like the gas concentration, you can see that the color remains constant, or if it was like an aqueous system, you would be able to do a titration or something to figure out the concentration. So that is a macroscopic property and it remains constant.
Now, something to point out here is that just because the concentrations of the reactants and products are constant while at equilibrium, does not mean that they're the same as each other.
Did you guys get that? What is equal at equilibrium? Rates, forward and reverse rate. What is not equal at equilibrium? The concentration of the products and the concentration of the reactants. So you're going to see little diagrams here where the amount of products get bigger or smaller depending on the conditions of the equilibrium.
For example, there could be lots of ammonium chloride and only a small amount of ammonia and hydrogen chloride.
So this would be a situation where you have lots of reactant, but not very much product. Yes? And actually, because we can, I'm going to add this in here. Let's go to here. Let's go to here. This one, nope, that one. There we go. Okay, so you can see in our little picture here, Did I swap the order of these? Probably. Anyway, if you have more reactants than products, the ratio of reactants to products will stay constant. And this is going to become something that we will talk about later in the unit. And it is called, if we take the concentration of the, if we take the concentration of the products and we divide it by the concentration of the reactants, we get a ratio, yes? At equilibrium, does that ratio change? No. At equilibrium, this ratio is constant. And you might say to yourself, Ms. Spence, why did you spell constant with a K? And it's because this ratio of product concentration over reactant concentration is called the equilibrium constant. I'm still going to spell it with a K. And the reason for that is that we give it this symbol K for constant, and then a little EQ at the bottom for equilibrium. And the whole second part of this unit will be talking about those ratios and doing math with those ratios. Okay, but for now, you just need to realize that when you are at equilibrium, that ratio remains the same. And you can have a small number. Small products over big reactants gives you a small number. But if we go up here and we have a large concentration of products over a small concentration of reactants, is that going to give us a small number or a big number? That gives us a big number. How about down here? This one would be a small number. Yes, because we have a small number over a bigger number, that gives us a small number. So this ratio here is called the KEQ. Okay? Brilliant. All right. Are we ready? Okay, back to the video. Here we go.
Or there could be lots of ammonia and hydrogen chloride, but only a small amount of ammonium chloride. In either case though, as long as the forward and backward rates are the same, then the reaction would still be at equilibrium. However, what would change when we have these different concentrations is the position of the equilibrium. When there are more products, like this, we would say that the equilibrium lies to the right. But if we had more reactants...
Hang on one second. There we go. So if we have a reaction like that, we say the position of the equilibrium lies to the right because we have more stuff on the right. And that concentration will remain constant. And that ratio of products to reactants will be big. Okay, but it will be a constant value. It will not change. Now let's watch what happens as we go the other way.
When there are more products, like this, we would say that the equilibrium lies to the right. But if we had more reactants and fewer products again, then we'd say that the equilibrium lies to the left.
Okay, so here we have the equilibrium lying to the left. So we have a small amount of product over a big amount of reactants, which means that that KEQ value will be, think of a small number, like 1, yes? Think of a big number, like 100, yes? 1 over 100, is that a big number or a small number? Small number. So if you have a small number over a big number, that's going to be a small number. So if it lies to the left, you will have a small KEQ. If it lies to the right, you will have a large KEQ.
This position of equilibrium can change depending on the conditions. For example, adding heat to this reaction encourages the forward reaction, meaning we'll have relatively more products, as the position of equilibrium moves to the right.
Okay, so did you see that? We added some heat, and what happened? We made more product. Just like when we added heat to the system that was in our demonstration, what happened to the color? When we added heat, it became more brown. It became a darker brown, so it shifted towards the direction with that brown color.
On the other hand, if we cool the conditions of our reaction, it would push the position of equilibrium back to the left, so it would have more ammonium chloride again.
Okay, so we have now cooled it, and now we have a lot of ammonium chloride, so that's our reactant, and not very much of the product, so now we have a small number over a big number, all right, and that is what happens at a cold temperature. Now, how the temperature affects the equilibrium is going to depend on whether you are writing the forward reaction as the endothermic reaction or the reverse reaction as the endothermic reaction. We'll talk more about that later, okay? But don't be like, oh, every time I increase the temperature, it shifts towards the products. I end up getting more product, because that is not true, okay? So don't make that generalization.
Regardless of its position, though, equilibrium can only be reached if the reversible reaction is done in a closed system, which means some kind of sealed environment from which none of the reactants or products can escape. Because if the products kept escaping, it would never reach equilibrium. The last thing we need to cover is that reversible reactions are always exothermic in one direction and endothermic in the other. For example, in this reaction, which shows the thermal decomposition of hydrated copper sulfate to anhydrous copper sulfate and water, the forward reaction is endothermic, and so the backward reaction is exothermic. If you're not familiar with these terms, hydrated just means that water is present, and anhydrous means that there's no water.
Do you remember doing a lab like this last year where you had a crystal and you heated it and it lost some mass? Okay, and if you were in my class, we definitely did it with copper sulfate because I don't like doing a lot of work, and it's blue, this beautiful blue crystal, and it turns white. Okay, so basically you've got the water within the crystal, and the water all comes out of the crystal and turns into this anhydrous salt, and the water escapes off into the atmosphere. Now, if you have this in a closed system, you put a lid on it, then the water will equilibrate and will bounce in and out of the crystal.
Now, because the forward reaction is endothermic, it requires heat energy from the surroundings to work. So if we were to heat some hydrated copper sulfate, which exists as blue crystals, it will drive the reaction to the right, which evaporates off the water and leaves white anhydrous copper sulfate powder. If we then took away the heat and added some water to this powder though, it would drive the backward reaction, so the equilibrium would shift to the left and reform our blue crystals of copper sulfate. And because this reaction is exothermic, it would re-release all of that energy it had just absorbed in the forward reaction. So to quickly recap everything, reversible reactions are those with a double arrow in the middle, which shows that they can react in both the forward and backward directions, one of which will have to be exothermic, and the other endothermic. And if these two rates are the same, then we say that the reaction is at equilibrium, and the concentrations of the reactants and products will remain constant. The position of equilibrium can change though, and will shift to the left or the right depending on the conditions. Anyway, that's all for today, so hope you enjoyed it, and we'll see you next time.
Okay. So now we're going to talk about that reaction that happened in the fume hood. All right. So get yourself some blank paper. Okay, before we start on that particular reaction, we are going to make a couple of definitions. First one is a stress. Okay, and a stress is something that we do to a system. In other words, a change in conditions. So for example, what did we do to that system over in the fume hood? We had the two flasks. What did we do with them? We changed the temperature. So for example, a change in temperature. Now, systems are at equilibrium because the forward and reverse rates are equal. What a stress does is it changes the rates so that they are now unequal. So a stress changes either the A, forward rate, B, the reverse rate, or C, what else could it do? It could change the forward rate, or it could change the reverse rate, or it could change both rates. And the last part of that one is that so that the two rates are no longer equal. So the forward and reverse rates are no longer equal. That is a stress. The other word that we need to define is a shift. And a shift is the response of an equilibrium to a stress. A system can shift to the right and if we're shifting to the right, are we making more reactant or are we making more product? We're making more product because remember we have reactants, products, and if we're shifting to the right, it means we are making more products and using up some reactants. What would the converse situation be, the opposite situation? A system can shift to the left and if we're shifting to the left, which way are we going? From right to left, towards the reactants. So in other words, that's what IE means. Anyone interested in what IE stands for? No, I'm going to tell you anyway. IE stands for id est, which is Latin for that is, which means in other words, i.e., in other words. So if you're like, what is this IE business? IE means id est, that is, it means in other words. Right? And now you know. I could explain this one too. This is my abbreviation for with, but I don't want to because I don't want to write the word. So you can look up that abbreviation on your own. All right. So a system can shift to the left, and in other words, we would be making more what? Yeah. Reactants. and we would be using up products. If we are shifting to the right, which rate is faster? Forward or reverse? Remember, we're making more product. If we're making more product, which reaction is faster? Forward. Because we're making, like if I'm pushing things this way, I'm pushing them that way quickly. And if I'm the reverse reaction, I'm kind of like, la, 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 la. Where do I end up with more stuff? If I'm going like this, la, 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 la. What do you end up with more of? Oh, did I go the wrong way? No, that's right. That's right. I'm making more product, yes? So the forward, if the forward rate is faster than the reverse rate, I will make more product. Okay? And if we are shifting to the left, which rate is faster? The reverse, right? So if you think about that situation again, if the reverse rate is going fast, and your products are over here, and the forward rate is going slow, what are you going to end up with more of? You're going to end up with more of the reactant, okay? And you can draw this, you can actually show using the equilibrium arrows that the forward rate is faster than the reverse rate by showing the size of the arrows as being different. And if we're shifting to the left, then the reverse rate is faster. Now in our demo, we had, let's see if I can actually find a brown pen. That would be exciting. Oh, there we go. That doesn't even look brown, it just looks gray. NO2, which is brown. Okay, and we have two of them in equilibrium with N2O4, which is colorless. So what did we do first? First of all, we increased the temperature. Okay, I know we decreased the temperature at the same time, but we'll look at that later. We increased the temperature. What do we call that when we do something to a system? That is our stress. What did we see when we increased the temperature? Did it get darker or lighter? We saw a darker brown color. Would you like me to say we saw a darker brown color evolve or a darker brown color develop? Develop? Okay. And then stabilize. What process was happening, one of our new words, when the darker brown color was developing? We had our shift. And what about when it stabilized? This is an old word. We are now at a new equilibrium. With a different position, okay? In this case, it would be a new equilibrium that lies more to the left. So in other words, i.e., id est, that is, the system in response to an increase in temperature the system shifted which way? Left. I was going to write black. It's colorless. It's hard to write colorless pen because it doesn't write very well. Now I have a question for you. What happens to the forward rate when we increase the temperature? Don't think too hard. Think about what you would have written last Friday. When you increase temperature, what happens to rate? The rate increases because the particles are moving faster, they collide more frequently, and they collide with more energy. Therefore, a larger percentage of collisions will have sufficient energy to collide successfully. Okay, so when we increase the temperature, the forward rate increases. Next question. What happens to the reverse rate when we increase temperature? Does the rate increase, decrease, or stay the same? And don't think too hard. Think about how you would have answered this last week. When you increase temperature, what happens to rate? The rate increases. So when you increase temperature, both the forward rate and the reverse rate increase. But if we are shifting to the left, which rate had to have increased more? Tell your partner that one, okay? Have a chat with your partner about that. Since we are shifting, which rate must have increased more? The reverse rate. So if we were to have our original rates, we could represent them like this. Yes? So our original rates would be like that. And then at increased temperature, we're going to end up with like this. The forward rate is going to increase, so the arrow got bigger. But what happens to the reverse rate? It gets bigger, but even more bigger. Yes? Is good? I'm going to quit switching colors. I'm just going to make it all black. It doesn't matter. To brown. Or colorless. So we are now shifting. As we shift, what happens to the concentration of NO2? Concentration of NO2 increases, yes, because we are making it faster than we are using it up. As the concentration of NO2 increases, what happens to the forward rate? Chat with your neighbor about that.
As the concentration of NO2 increases, will the forward rate increase with the increase? I think it increases because of more of it. Yeah.
So we've got more reactant particles, yes? What will happen to the forward rate? The forward rate will increase because the more particles you have, the more collisions you have, the rate will get faster. So as NO2 in concentration increases, the forward rate increases. As we shift, what is happening to the concentration of N2O4? it is decreasing because you can see we're using it up faster than we are making it. As the concentration of N2O4 decreases, the reverse rate does something. Chat with your neighbor about that. What's going on? I have fewer product molecules. What's going to happen to the rate of the reverse reaction? It's going to decrease because there's fewer particles, therefore there are fewer collisions, therefore the rate will decrease. So the reverse rate decreases. So now we go from the shifting arrows becomes, what's going to happen to those two arrows? They're going to become equal. The forward rate is going to increase, and the reverse rate is going to decrease until the two rates are the same. And at that point, you will be at your new equilibrium, new dynamic equilibrium. And if I were to ask you which direction is endothermic or exothermic, I don't know if you guys caught this from Friday's lesson or remember it. Which rate is affected more by a change in temperature? Endothermic is affected more by a change in temperature. Which direction is endothermic? Remember, our original rates were like this. And then we had our shifting rates, which were like this. Both rates got faster, but which one got more faster? The reverse rate. So that would be our reverse rate. The reverse rate got more faster. I know that's terrible grammar, but I'm going to say it anyway. Both rates got faster. But the reverse rate got more faster. Therefore, the reverse reaction is endothermic. And that is it for today. And your only homework, because we did this lesson in the correct order this time, this was a much better lesson than block 7. You don't have to do any of this, you just have to do page 15. Okay? Very short homework tonight. Very, very short. Enjoy it. It won't happen often. And your test will be marked by the end of the week. I will not make any more guarantees than that. I will try and have it done earlier, but like I said, I will not make any guarantees.
Yeah. No.